Good morning, everyone. As usual, we'll start our tutorial with the quiz test at 11:10. Are there any questions before we start the quiz? If you have any questions, please post in the chat. As usual, the quiz will be 15 minutes. So we start at 11:10. You should be done. Most of you should be done by 11:25. And then we finish up with a few more examples on how to use caches and how the cache performance varies with different configurations from the last class. And then we're going to have some time, and I will be happy to answer questions individually for people that want to catch up with the material or have some general questions. Okay, so the test should be available for you now. Please start it and return back at 11:25. Good luck with the test. See you soon. Okay, I hope most people finished their quiz, so we can start now. As usual, please, if you can turn on your camera, that would be very helpful. Can someone confirm that you hear me well? Okay, thank you, guys. Okay, so let's start. So the plan for today is mostly to finish the lecture on caches and to go over a few tricky examples to see how the caches operate. Okay. So remember, we finished the Wednesday's lecture on discussing how the caches would operate when you vary the block size, associativity, and the size. And let's vary some of those parameters. And again, to remind you how cache works with the basic replacement policy, I will go you through the sequence of addresses again, similar to the end of the lecture, and then we go through a more complicated example. In this example, we assume we had a direct map cache that stores 4 words. Direct map means that every address is mapped uniquely to some block. So essentially, there is no there is only 4 sets there, right, which all stores 4 bytes, right, 4 words, right. Doesn't have to be 4 byte, but let's assume 4 bytes for simplicity. And that's what represented by these short addresses. In reality, those addresses might be much longer, but to simplify the time, I just took the last few bits. Okay. So the first thing to remember is that when we get the address, is that the last few bits of the address is going to define the offset of the data in the cache. So for example, the other bits are used for the tag. So what happens here when we have an address 40, right? We look at the last few bits, and in this case, I need to look at the last, essentially we had 4 blocks, right? So essentially, the last 2 bits tells me the offset within a block, 4 bytes. So it's 2 bits, and 2 bits are used for indexing those sets in the cache. So essentially, the last 2 plus 2, 4 bits, which is half of the bytes, which is exactly 0, I use as an index. So essentially, everything, if you take 0 and remove the last 2 bits, the last 2 bits and look at the middle 2 bits, they're all 0. That means you map into this block. Okay. Any questions here? So does everyone understand how the mapping happens in the cache? Okay, Terry asked, I don't understand what you mean by the last 4 bits. So let's take, instead of 40, let's take a different address, say 44, right? So Terry, if you look at the essentially, or you know what, not even 44, let's look at 42, right? So if you look at address 42, right, remember I said we only care about the last 4 bits, right? The last 4 bits for address 42 in binary would be 0010. Is this clear? Yes. So the last 2 bits, 10, this is just offset within a block. So 42 means somewhere in the middle here, I'm going to store this, right? But the pre-last 2 bits, 00, tell me the index of the block I want to use. So what I do when I had the address like 42, I apply a mask on it. So I do AND with essentially, if you write in C, that would be 0010. So I apply this mask. It's such a mask. So when I do, it should be, if you write in C, it should be double AND. Sorry, it should be 1 AND if you want binary operation. But essentially the point is I get rid of all the bits that are relevant and only look at the bits that matters. And then I shift those bits also, right? And then if you look at those 2 bits, right, that gives me the index of the block among the sets. Is this clear? So you throw away all the front-end bits because, okay, so this is a mask. So this is the mask that tells me I only want 2 pre-last bits, right? This is what I was talking in the last lecture about the masks. So the masks tells me I don't care about all the front-end bits because this is just the tag. They don't affect where the block is mapped. And the last few bits are relevant because they just offset of the block of their bytes within the block. So for example, this the block. So essentially, if you had an address that ends with 00, 01, 02, sorry, so it's going to be 00, 01, 10, 11, they all gonna map to the same block in the cache because this is just offset within the block. So the last 2 bits are not needed. Everything at the front end is not needed. So this mask, which in the binary is essentially 1100. You can think about it as having many zeros here, right? So this mask selects only the bits that are relevant. The last 2 bits are not relevant to the index because remember, if you're going to map 40, 41, 42, 43, they all map to the same block. They all stored still in this block, right? So the last 2 bits just shows you the offset within the block. So when you look at the address, I take the address and I throw away the offset, that's the last few bits, and I remove the front end. That's the bits that represent the indexed among the sets, right? So all these 3 addresses maps still to the same block, but they're going to be located at a different location. So Joan, which? Okay. So I guess not that many people got then when we already have the last 2 bits. So what does the index mean in this case when we already had? I try to ask Jonathan's question for what the index mean. Remember, I need for each address find where is it located in the cache. What I'm telling you is for that to happen, first I need to get rid of all the front end bits. So I remove everything except for the first 4 bits, right? Because that doesn't affect, you can think about it as things being rolled over. I start with the address 0, it maps here. Address 4 maps here. Address 8 maps here. Address 12 maps here. And then I go over and I go like, 16, 20, and so on. So the last 2 bits, they are not help you to find the index. They represent their offset because you can have address 0, 1, 2, 3, right? They all will be within the same block. So if I need just to find your index, what I need to do, I need to remove all the bits except for the last 4. And then from the last 4 bits, I need to remove the last 2 bits. So the 2 bits in the middle are the one that give me their number of set or an index in the cache. Jonathan, did I answer your question? I think I just gave an example. Okay, so let's say we had address 42. Is everyone following me, right? That's the address in hexamal, right? So if you look at that address, the first thing we do, we get rid of the front end bits. So we throw away all the bits except the last 4. So for 42, the last 4 bits, as Terry just said, 4401. So we remove the last 2 bits, we get 00, and the index is 0. So it means that if we would get something like 42, it would be in the middle of this thing, right? And the index for it would be 0. Is this clear to everyone? So Jonathan, you want an example. Is the 42 example is making clear to you? So Sam is asking, why use fourth and third bit to last instead of second and first to last? So think about contiguous memory stored. So when people store in their memory, they store something, say at address 0, then an address 1, 2, and 3, right? So essentially, then you want those bytes being contiguous, right? So starting from 0, you want the next byte being 0. So the first few bits in the address represent the offset within the block, right? So that's why I need to mask out the last few bits to represent the size of the block. Yes, that's sequential data, yeah. Jonathan says you convert 42 to binary. Yes, so 42 hexamal binary, it's the same thing. It's just when you use mask, it's the same thing. But if you look at 42 as in the binary format, the last 4 digits are the ones that represent 0010, yeah. Stores 4 words means each block stores 4 values. What it means is that each word is 4 bytes. So essentially, and I have 4 4-byte words. Okay. And in general, like I gave you examples of addresses, 41, 42. In reality, processors doesn't have those addresses because that's very inefficient. So all the addresses are going to be aligned to 4 bytes. So you don't gonna usually see the weird addresses like 41 or 42, okay? So in a 32-bit system, addresses are aligned to 4 bytes usually. Okay, I hope we covered everything. Let me now go step by step, right? So the first thing we're gonna do, we're gonna map 40. And 40 gets into the first block. Is this clear with everyone? I think I covered that multiple times. So you see why 40 goes in the first block, right? Anyone has any issues with that? Okay. Okay, so then we get 48. If you look at address 48, you convert it into the binary, do the math that we discover, you're going to find that it needs to map to this block because 40, so essentially if you end with 0, you go to the first block. If you end with 4, you go to the second block. If you end with A, you go to a third block. If you end with C in hexamal, then you're going to get to third block, okay? Is this clear to everyone? There is no such thing. Don't trust Google on everything. Word can be defined by a machine. So if your machine is 16-bit, then the word is 2-byte. And word can mean different things. If you're using a 32-bit machine, the word is 4-byte. Here, the word is 4-byte for simplicity, right? But in a 64-bit system that most of your laptops probably are, the word is 8-byte, right? Word can vary, okay? Okay, so let's move on with the example. So then we got 4C. So 4C maps to fourth block that marks as 3. Then what happens, we're going to get another 40. You see another 40, it's already in the cache. It means that if I want to read something from this memory, we are lucky it's already in the cache. So all these 3 cases were misses. The data was not in the cache yet. We just brought it in the cache, but now it's in the cache. That's the only hit in this trace, right? So 40 access results in a hit. So what happens next? I had an address 50, and it's a direct map cache. 50 has to go here, so it has to evict 40. So even though later on in the future we had another 40, we would love to keep it around in the cache. We can't because it's a direct map cache. So 40 is kicked out. Then after that, 58 comes, it kicks out 48. 5C comes, it kicks out 5C. And then 40 comes again, And sorry, it's gone. So it's not a miss in the cache. Is going to kick out 50, but it's going to be a miss again. And you're going to bring 40 from memory again for the third time. And then 60 comes. It's a 60 comes and evicts 40 again. Then 48 comes, and then 4C, 4C comes, and it evicts here. And then you see 44 comes. And 44 comes, and it occupies that block that was fully unutilized all this time. But because it's a direct map cache, no other address could go into here. And this was a waste of space for a long time, but there's nothing we can do under direct map cache. And then we get, 40, 60 again, right? They all go to this block. They all result in misses. Then 58 and then 5C. So even though I've seen address 58 before and I've seen 5C before, I cannot benefit from that, right? Because there was just not enough, space in the direct map cache. Okay, is this clear with everyone? So the result is, even though, let me do the count, 1, 2, 3, 4. Yeah, so 16 accesses, and there was only one hit. Everything else was a miss. So as you can imagine, this is not particularly impressive cache design. So Muhammad asking why is 4.4 has an index 1. Okay, so if you look at 4.4, remember the first thing you do, you throw away all the bits except the last 4. So Ivan says it's what? No, Ivan, you're not correct. Yes, it's 0, 1, 0, 0, right? 4.4. Right? So your index, sorry. So for 4.4, yes. So it's essentially, and then you remove the last 2 bits, you get 0, 1, and that becomes 1. Okay. Okay, good. So we got this example. Okay, any questions here? Okay, so you see probably that this cache is not operating particularly impressively, right? We create it, we put hardware on it, but it's mostly misses. If we're missing the cache, there's no benefit of having it because we don't bring the data any faster. The whole point of having cache is to bring data early, quicker from the memory, because the cache would take a few cycles and the memory takes hundreds of cycles. But if it's a miss, then it's not helpful. So we want to have as many hits as possible. So let's look at a few examples how cache can be improved on different dimensions. And I'll give you some home exercises to try it on your own more. So now imagine that we want to, we would now have a direct map cache, but now each block stores 2 words. What does that mean? It means that when I remember that spatial locality. So I bring 1 word, I bring a JSON word as well, based on the simple addressing. So what does it mean physically? So instead of having 4 sets, right? I'm gonna have 2 adjacent blocks. You see it, right? So that's a change in configuration in the cache. So now I'm only gonna have 2 sets, right? Every time I'm gonna bring 1 word, I'm gonna bring an adjacent word as well, depending on the address. So that's the difference. It's still direct map, but I bring more data than I need because we believe spatial locality is a good idea. This is how your current caches are organized. So when you read 4 bytes from memory, you actually read the whole 64 bytes from memory. But for simplicity, for this exercise, I only keep 2 words. So let me quickly show how much better that's going to be. So let's look at 40. So whenever I read 40, right? Again, remember here I only had 2 indices. So when I'm going to do the address logic, it means that, so essentially this thing goes here, right? and the next 8 bytes go here. So let me explain again. So when you bring 40, you do the same math before, but now remember is that the number of sets is only 2. So I only keep the last essentially, so I still use 4 bits as before of my address, but now 3 bits I use for offset and only 1 bit I use for index, because the index is only 0, 1, right? So there are 3 bits of offset, right? And 2 bits and 1 bit for index. So you do the same mask, you remove all the bits except the last 4, but only the first bit now, only 1 bit of this 4 is used for index. Is this clear to everyone? So when I bring 40, it takes its block, but also I automatically bring the block 44. It also comes into the cache. You didn't ask for it, but I bring it automatically because that's how I design my cache, right? I bring more memory. So any questions here, because that's important. So question by question, Sam's question, how do you keep track of which data is, what is FL? Oh, how we track first in, first out? That's a special date. A very good question. That's how you keep the metadata. Just right now, assume you know how to keep it. It's actually very simple, right? You just pick a recency bits, and when essentially something new is coming, you just update it, right? And for direct map cache is trivial, right? So it just like it's something new coming, you only had 1 target to remove, right? So it's a trivial, first in, first out is trivial. When we're going to have associativity, it would be less trivial. So for example, if you had a 2-way associative cache, you had an index saying this was the freshest block and this is just 1 step older, and you just need to pick between the 2. So this is, you don't need to worry about it right now. There's an implementation. Jonathan asks, how do you decide it brings 44 and now doesn't bring 45? Remember, Jonathan, 44 just means the start of the block. I bring all the bytes from 40 to 47 here. So this is just the first 4 bytes that I really ask for, and that's the next 4. So it has 40, it has the memory and the address 44, 45, 46, and 47. Jonathan, did I answer your question? This is just to highlight this fact. Each of these blocks has 4 bytes. Okay, so Jonathan, did it answer your question? Yes, the block 40 contains 4 bytes. It's a word. Word has 4 bytes. I just cannot write individual bytes here, so I just bring you the whole block. And block 44 contains 44, 45, 46, 47. That's correct. You don't bring 1 byte. You bring all the data corresponds to that byte, to this address. Yeah, 2 blocks were stored at once. That's correct. Okay, anyone has any question? Again, Sam, you ask a very good questions about how you're going to store different bits for different replacement policy. This is something I can cover one-on-one if you're really curious, because that's too many low-level details. But essentially, the best way to think about, there is an index, there is a counter. So whenever you bring something in, you put the counter to the maximum value. It means the most recent. And then as you bring something else to the same set, you decrease this counter, right? So for direct map cache, that's super trivial because you always replace one with the fresh copy, right? And you remove the other one, so you don't really need to even track anything. For 2-way associative cache, you need to have a 1-bit index that says it's the earliest arrival or 1 step. Oh my God, so what does 2-word means? 2 words means is that if the word is 4 byte, I mean, if I had an address 40, I bring 1 word corresponds to this 4 bytes and another nearby word 44. Okay. Let's go through the example any further. Is it clear what happens here? Why 40 and 40 in the same block? I think I explained multiple times. We had 2 blocks of 2 words stored together. So if you want to bring one of them, you had to bring the other one. This is how the cache is designed. How you determine how many bit offsets are there and how many bits are for index? Great question. So if my block here is 8 byte, it means that offset here needs 3 bits, right? It needs 3 bits because I need to distinguish between every byte here. So it means 3 bits goes for that. So you need 3 bits for offset. And I actually put a formula for that on the slides on Wednesday. Then I only had 2 sets here, 1 and 2. So I need 1 bit for set number. Set number is an index, 0 or 1. So a total number of bits I need is 4. Jonathan, does it answer your question? Okay, you said you understand the 3-bit offset. So remember now, like you look at your cache configuration. Our cache has 8-byte blocks, 2 words, and it has 2 sets, right? So to figure out whether I should use set 0 or set 1, I just need 1 bit. If I would have 4, I would need 2 bits. If I would have 8, I would need 3 bits, right? So this is how I define. So essentially, address directly tells me where to go. I just need to read the address carefully. So essentially, you take the address, the lower bit are your offset. How big is the block? Then how you determine each row is 8 byte? Because I said in the beginning, the cache is built to have 2 blocks of 2 words. Each word is 4 bytes, as we defined on the previous slide. So 2 blocks of 2 words is 8 byte. Okay. Okay, let's move on. So I hope I answered all the basic questions, what to move. So when 48 arrives, right, we do the usual math, and we found that it has to be here, which is not a surprise, right? Everything from 40, 47 maps here, then 48 maps here. And by no surprise, the adjacent bits arrive here as well. So when I request 48, 8-byte arrives, not 4, okay? Why is this good? Because as you can see later on, I also request 4C. And oh my God, now this 4C already in the cache. So I'm gonna access this guy. I already have it here, and that's gonna result in a hit in the cache. So if you keep track on somewhere on the piece of paper, because I did it already myself, this is gonna be a hit. Then I'm gonna look for 40. 40 is already, so that's gonna be the second hit, right? So that's both already in the cache. Then 50 arrives, and 50 is not in the cache, and there's no space for it. So I need to remove everything associated with 40. So 50 and 54 comes into the cache, evicting those 2 blocks, because I always bring 8 bytes. Any questions so far? So we are right now here, we just brought 50, and we had 2 hits already. So then 58 arrives, and the same way it evicts what's in the cache right now. Then we request 40 again, right? And 40 is not here, so that's a miss. And 44 also arrives together with it. And then we request 60, so 60 comes, evicts 40. And then 48 comes, right? And 48, when it comes, it brings 4C with it. And you see we had another 4C here, right? So that results in another hit. Then 44 arrives. 44 is by our rules supposed to bring adjacent memory. So when 44 arrives, it also brings 40 with it, because it doesn't necessarily mean things that follows it. They bring whatever belongs to their consecutive 8 bytes. So you might bring something in the middle, it's going to bring the same 8 bytes rounded, right? So when 4C comes, it brings 40. 4 comes, it brings 40. So when the next 40 comes, it's again a hit. So again, one more hit. And then 60 arrives, that brings 64, those all misses. And then 58 comes, 58 is going to bring, you know, both 58 and 5C. So when another 5C comes, it's again a hit. So if you carefully look, you're going to get, if I didn't make my math correct, so 16 accesses, now you get 6 hits. Okay. So makes one ask, what if 41 arrives? First of all, I said 41 cannot arrive because everything is rounded to, you know, to 4 bytes here. But even if it would be possible, we always round everything. So we take 41 and looks at which 8-byte consecutive it belongs when you mask out the last 3 bits. So 41s would bring everything from 40 to 47, 42, 43, no difference, right? It means if you belong in that consecutive 8-byte of memory, that's what I'm going to bring in the cache. Whether it's a first byte, second byte, 7th byte, doesn't matter. It brings the same cache line. A miss occurs when you bring something, you ask for something and it's not in the cache. For example, that we already did it on the previous slide. It's not already stored in the cache, so it's not there, it missed, I had to go for memory. Yeah, Jan answered correctly, so that's the whole point. So the whole point is to have a hit, not a miss. Okay, so I hope we covered this quite accurately. On the next slide, because I need to go for my next meeting soon, I leave you a few more examples to practice at home. And if you cannot figure it out, you can try it and post questions on Piazza. But essentially one thing is a two-way associative cache that stores 4 words. So the difference in this cache is that two-way associativity is different from bringing 8-byte together. It means I have 2 sets, but whenever I bring data, I can place them either here or here. I have freedom on where to place the data. So I want you to practice this out. So essentially what's going to happen when I bring, say, 40, it maps here, 48 would map, you know, to the other one, but then essentially you're going to start to get collisions. So in the, remember in the direct map cache, you always have only one thing to remove. But here you had multiple things to remove. So you need to decide which one based on the replacement policy. And your replacement policy is first in, first out. Okay. So I'll let you guys try it out at home and bring questions if you have. And I leave another slide with a different replacement policy, right? And you can try to change configuration on your cache to see how the hit miss rate will change. No, Sam, the top level won't be 0.7 anymore. Two-way associative, but we assume 4 different words. So each of these stores 4 bytes independently, right? So essentially 40 to, say if you bring 40, it's going to just take one of these blocks. Then I bring 48, it's going to take another of this block. Then 4C will comes, but so let me show quickly. So 40 comes, I bring just 40. That's it, because both blocks are empty. When 48 comes, it's going to map in here, right? Because it's 40, 44 goes here, 48 goes here, 4C goes here. So 48 is going to take the next free block. Then 4C comes, it's going to come here. And when 40 comes, it's going to be a hit. And then 50 comes, it has to take place of one of those blocks. And essentially, because 40 comes early, first in, first out, so 50 is going to take the space of 40. Sam, is this clear? So the indexing formula now is different because now we have 2 bits used for offset, then we had 1 bit used for which set to take, and there is 1 bit is used, you know, So that's it. There's only 3 bits they identified, and the way is flexible. So right now, when you're going to take your address 48, right, you're going to look at the the last 3 bits, and the last 3 bits are going to be 0. So essentially, it's going to be 000 448 in the binary form. So it maps the same way as 40. But now you had a freedom. So physically, you had the same amount of space, but how you manipulate the space is different. Okay. Any questions? What will be replacing the original one depends on the previous order. Absolutely correct. And you defined it as a replacement policy. Here is the first in, first out replacement policy. Very simple. So if you had 2 blocks here, 40 and 48, and then 50 arrives, you just look what was early. 40 was early, 48 was late, so you remove 40 first. But you can have other replacement policies. So what are the 2 sets in the diagram? So there is one set here, and that's another set here. So you said this time it is a 3-bit for offset, 1 bit for index. No, this time is 2-bit for offset and 1 bit for index. So I only care about the last 3 bits total. Before I cared about 4 bits. So every time when you define the shape of the cache, you will need to redo the math and see how many bits here. So here, these blocks are treated independently from each other, because the offset within a block is only 2 bits, right? It's 4 bytes. Those things you see are now disjoint. They disjoint from each other. I can store something in here or something in the nearby, but the indexing for them is the same. So essentially, I need the index bits to figure out which set to go, and the offset within a block, but whether take first or second one is independent from your address. So the previous slide was using, that's what I asked Ryan's question. The previous case was benefiting from spatial locality, right? I was trying to keep more bytes around. What I'm doing here, I'm trying to benefit from temporal locality. So I try to keep more useful things around, right? So, and I don't want to kick out things immediately. That's a problem with direct map caches. So direct map caches, if something maps to the same block, they're going to kick out each other. So the hit rate is very poor. In the previous slide, I show how you benefit from spatial locality to bring more data around. Here we scratch that, we don't bring more data, we just look associativity separately. Then in the real caches, you're going to have both associativity and larger blocks. Okay, any other questions? Each set here, you can think about it as a queue, right? It's independent from each other. And yeah, so you don't, addresses don't identify whether they go in way 0 or way 1. So essentially this is set 0, set 1. And this way is way 0, way 1. Hardware has a freedom where to put what based on the replacement policy. Sam, did I answer your question? Okay, so I think I'm over time right now. So thanks everyone. I hope I answered a lot of questions. I leave those slides already available for you since Wednesday, so you can take and play with them. And remember, don't be limited what I did. Replace things, make it 4-way, make it both, spatial and temporal locality at the same time, and see how many hits you're gonna get. So please practice yourself. I'll leave you a few more examples on the slide deck so you can practice. Okay, thank you guys. Thank you. Jonathan, I had a meeting right now. But if you send me your questions on Piazza or anything, we'll figure out where to meet. But I had to run right now, sorry. Okay, thank you guys.